Hello everyone, good morning. I have my coffee, I hope you have yours as well. Today I'm going to give you a little bit of background about approximation algorithms, and I know in your summer school you've been learning a lot about different kinds of algorithms, minnow spanning trees, matching, shortest paths, data structures, things like that. In general, most of the problems that you've been learning about in algorithms have the property that most of these algorithms that you've learned are actually fairly efficient algorithms. So for example, a lot of the problems that we want to solve have to do with graphs. So we might have a graph and we're trying to say find the shortest path between some fixed pair of vertices S and T, and the question is computationally how do we do it? Some of the algorithms that you've seen until now are either all pair shortest paths or Dijkstra shortest path algorithm. All these algorithms have the property that they run in time polynomial in the input size. So if this graph consists of say n nodes and say m edges, then most of these polynomial algorithms might have running time of the form order of, let's say, n square multiplied by m, the number of edges, right? So these are polynomial functions of the size of the input. Unfortunately, there are many problems for which we are unable to find algorithms with that running time. And I'll give you some examples in a few minutes. So for example, if you want to find the shortest path, we know how to do that efficiently. But if I wanted to find the longest simple path in a graph between a pair of vertices, nobody's been able to find a polynomial algorithm for that problem. So this leads to the general topic of how difficult are these problems, because it looks like for none of them we are able to develop polynomial algorithms. So until now nobody's been able to find a polynomial algorithm. So this led to the wonderful theory of NP completeness. And the theory of NP completeness, in some sense, explains a little bit why some of these problems are difficult. In the sense that, so some of this you've already seen, problems in the class NP have the property that even though we cannot find a solution in polynomial time or test some kind of property in polynomial time, the problem has the property that if somebody claims that the answer to this question is yes, then in fact there is a polynomial time checking algorithm. So one simple question might be posed as follows. I have a graph with vertices S and T, and I ask you something like, does there exist a simple path from S to T whose length is at least some given value L, right? So the question could be posed as, does there exist a path from S to T of length at least L, right? Now, I said earlier that we do not yet know of a polynomial time algorithm for this problem. But suppose the answer to this question for this particular graph happens to be yes, then if I give you a path of length at least L, then it's easy for you to check that path in polynomial time. You can check whether the path is simple, so no edges and vertices are repeated, and then you can add up the lengths of all the edges and make sure it's at least L. So the whole point is that this is the characterization for what it means for a problem to be in the class NP. Cook identified sort of a very basic and fundamental problem called satisfiability that you've heard about, and the satisfiability problem is the following. You have a Boolean formula, and you're asked whether or not this Boolean formula has a satisfying assignment. Now, of course, like I said earlier, again, this is one of those hard problems where nobody knows of any polynomial time solution. But if I do believe that this formula has a satisfying assignment, then it is possible for me to give you the assignment, and in polynomial time you can verify that this assignment is a valid assignment. You don't have to find the assignment, you just have to check that it's a valid assignment. So what Cook went on to show is that many of these problems that we have been working on and have been unable to develop efficient algorithms for, in fact have the common property that they're all equally difficult. Namely that if there is a polynomial time algorithm for one, then in fact that implies there's a polynomial time algorithm for all. So they're all equally difficult in the sense that solving one means all of them get solved. It also means that if I'm given faced with an unknown problem which I'm trying to solve, then I have an option of developing a polynomial time algorithm. If I can do that, that's great. Otherwise, I could try to prove the problem is NP complete. And what that would show is that this problem that we are unable to solve until now is at least as difficult as all of these other thousands of NP-complete problems that people have found and have been working on for decades, have not been able to solve. Okay? But that still leaves us with the question of, once I have an actual problem and we are unable to find a polynomial time exact algorithm, then what are the options available to us? So this leads to the idea of an approximation algorithm. So let's start with a slightly different example known as the traveling salesman problem, and talk about that for a minute. So what is the traveling salesman problem? The traveling salesman problem says that you have a collection of cities and you want to visit all of these cities. So this is the most basic form of the problem. Every pair of cities has some distance between them, so we can sort of assume that Dij tells us what is the distance from I to j. And this distance function could be a measure of length, or it could be simply a measure of travel time between a pair of cities. And what is the goal for the traveling salesman? The traveling salesman lives at some house somewhere, and this traveling salesman has to find a shortest possible route to visit all of these cities. Okay? So this is the goal of the traveling salesman. This traveling salesman wants to visit all the cities and then return back to their starting point. Okay? So this problem is known as the traveling salesman problem. And again, it was shown that for most interesting distance functions, this problem is extremely hard, even if you have n points in the plane and every point simply specified by its xy coordinate, and this distance function is simply the shortest path length or the straight line distance between the pair of nodes, even that Euclidean traveling salesman problem is NP complete. Now the question is what do we do given the fact that there is no known polynomial time algorithm for this problem, and moreover it's believed to be extremely hard. So here comes in the notion of an approximation algorithm. So a lot of people have developed different heuristics. So a heuristic is simply a rule that we use to come up with some solution. So a simple heuristic might be, for example, start from your house and then simply go to the nearest unvisited node. So if you started from here, you just look around and say, what is the closest city that I need to visit? I go there. And then I look around from that point, I go to the closest city from there that I have not visited so far. And I keep repeating this rule, and that might give you some tour. So that obviously is a rule that is well defined. We can analyze its running time and show that that algorithm runs in time which is polynomial in the input size. The question really is, how good is the quality of the solution, right? So this algorithm is guaranteed to find some tour, but we have no idea how good the solution is, right? And many of these algorithms are easy to either implement on a computer or even run by hand given some solution that we are trying to find, but we really know very little about how good the solution is. Moreover, what I mean is that suppose I'm able to find a tour of length 500. We have no idea whether or not this solution of cost 500 is a good one. Namely, we don't know whether maybe the optimum solution is only 499, which means that even if we spend exponential time, we're not going to have the ability to improve this solution by that much. Or maybe the optimum solution is of cost 10, right? We have no idea. So that's the situation with heuristics, and the way people analyze heuristics typically is to come up with a variety of different heuristics, take a variety of different input instances, and then run different heuristics on those instances. So for example, if I come up with 3 heuristics A, B, C, and I have a test data set of maybe 200 cities, this could be, for example, all the capitals of all the states in India, or the capitals of all the states in the US, or whatever we find as a data set, and then we try all possible heuristics, and every heuristic could come up with a solution of a different cost. And that is one way in which we could compare two heuristics to each other. Of course, that is not terribly satisfying, because again, it doesn't tell us anything about what the optimum solution is. So the notion of approximation algorithms, in a way, is an attempt to capture how far you might be from an optimal solution. So more formally, let's stick a little bit with minimization problems. So minimization problems are typically problems for which there are some constraints In this example, the constraints are that I want to visit every city exactly once. And given these constraints, we want to be able to find a solution of low cost. And the quality of the solution is simply measured by the ratio of the cost of the solution found by the heuristic or the algorithm divided by the cost of the optimum solution. Okay? So in other words, suppose I come up with some heuristic and the cost of the solution is 500, and somehow for that instance we know what the optimum solution is, and let's say the optimum solution has cost 250, then we would say the ratio between the cost of the solution and the cost of the optimum solution is the measure for the quality of the solution, and so we would call this a factor 2 approximation. So what is a 2 approximation? A 2 approximation is an algorithm that runs in polynomial time, and it comes with the following guarantee. The guarantee is that no matter what input instance you give this algorithm, we are always guaranteed that the ratio of the cost of the solution to the cost of the optimum is bounded by a factor of 2. So in other words, if the cost of the heuristic is 100, we don't know what the true optimum is, right? That's NP hard, and there's no polynomial time algorithm to find that. But if the algorithm came with a guarantee that the solution is within a factor of 2 of optimum, then we do know that the optimum cost is at least 50. It could be that the optimum cost is even 99, and the solution we found is cost 100, but we don't know that for sure. But it comes with a guarantee, right? And the whole goal is that I want to be able to improve this bound of 2 as much as I can. So for example, in the traveling salesman problem, I will next show you an algorithm where we are able to prove a guarantee that this cost of the solution is guaranteed to be no more than 1.5. Okay. So that tells you a little bit about the basics of the idea of approximation algorithms. But the main point is that what separates approximation algorithms from heuristics is that we want to be able to make such a guarantee no matter what input is given to the algorithm. It doesn't matter what the input is, this guarantee always holds. Of course, our algorithm will get lucky and find a solution which is the optimum solution. It's just that we don't know how to prove that that's the optimum solution. Now, one might say, why is this of any value? The reason this is of value is that most of these techniques that we come up with are actually, because we don't really know what the true optimum is, are methods for lower bounding the optimum cost. So in other words, if my heuristic is doing badly, or actually we don't even know how well it's doing, but it comes up with a solution of say cost 100, and I'm able to prove using these lower bounding techniques that we'll talk about, which are important in the idea of approximation algorithms, if we're able to prove that the cost of the optimum solution is at least 90, then it tells us something about how far we are from the optimum. So even if I'm allowed to expand exponential time at this step, then it knows that we're not going to be able to improve the quality of the solution that much. So most of the approximation algorithms are coming with certain lower bounding techniques, and I'll give you some simple examples to illustrate these lower bounding techniques in a minute. So let's go back and talk a little bit about our favorite traveling salesman problem. So in the traveling salesman problem, I want to show you exactly how to obtain this factor 1.5 or 3 over 2 that I mentioned. So this is an old algorithm due to Christofides from the mid-70s. I don't remember the exact year, but maybe around 1975. Now, the idea behind this algorithm is the following. In the first step, the algorithm says compute a minimum spanning tree, T. Okay. Now, this is a problem that you've all seen before, and you know how to find a minimum spanning tree. So maybe I will illustrate by a simple example of what is going on. So I compute a minimum spanning tree in the graph where the edge lengths simply represent the distances between the cities, right? So this is what a structure of a minimum spanning tree might look like. Okay. Now, of course, somehow we want to figure out how to convert this minimum spanning tree into a tour. So the next step of the algorithm is the following. Let S be the vertices of odd degree in T. Right? So in this tree, notice that every vertex in the tree has either degree, which is even, or odd. So let's try to mark out in this case what the odd degree vertices are. Maybe I'll change the graph a little bit and make it that. Maybe add this one. So which are the vertices that have odd degree? This vertex has degree 1, which is odd. This vertex has degree 1, which is odd. This vertex has degree 1, which is odd. This node has degree 4. This node has degree 4. So I'm marking out all the odd degree vertices here. That's odd degree, that's odd degree, that's odd degree. Okay. So the first observation is that all of these, the size of S is even. So if I look at the cardinality of S, there's an even number of odd degree vertices. And this is easy to prove. So the cardinality of S is even. So this I will let you think about and prove. But now the question is, how do we convert this tree to a tour? So in step 3, what we're going to do is we're going to find a minimum weight matching of S. Okay? So we're taking all of these red nodes in this picture and we want to find a minimum weight matching. A minimum weight matching is simply a pairing of all of these vertices in S, and as there's an even number of vertices, we know that they can be paired. And among all possible pairings, I want to find the one of minimum cost. So let me use a different color. So for example, a minimum weight matching might look like pairing this pair of nodes, maybe pairing this pair of nodes, maybe pairing this pair of nodes, and maybe pairing that pair of nodes. Right? That could be one possible minimum weight matching. Now, in the next step of the algorithm, we are going to think about the graph formed by taking the union of the spanning tree and the matching, right? So step 4 says G prime is the graph formed by taking the union of the spanning tree and the matching, okay? Now, what is the key property for this graph G prime? Notice that when I take the union of the matching on S with the tree T, then the degree of every red node goes up by exactly 1, because there is one blue edge incident on it and an odd number of black edges. So every red node will now have even degree, and for the nodes that were white, they already had even degree to begin with, and we never changed the degrees of those vertices. So now we get a graph G prime which has the property that every vertex has even degree. Why is this useful? This is useful because such graphs are Eulerian graphs. An Eulerian graph is a graph where every node has even degree. Moreover, it's connected, and it's connected because when we started off with a connected graph T, that we can find a traversal of the edges of this graph where every edge is traversed exactly once. So I can start from any vertex, and then I can traverse along this to find what is known as an Euler tour. And in this Euler tour, notice that we visit every edge exactly once, and then we return to the starting point. Okay? We are not quite done yet, because of course, while we are visiting every edge in the graph, notice that we are also visiting every vertex. The only problem is that we are visiting some vertices multiple times. So we want to avoid visiting some vertices multiple times. So for that, let's repeat the process, and we will simply skip over vertices when we visit them a second time. So I started here. Let's say I started at vertex 1, then I go to vertex 2, then I go to vertex 3, then I come to vertex 4, 5, 6, and now according to the Euler tour, I'm going from 6 to 4, but that's a mistake because we already visited 4. So we could ask the question, what is the next unvisited vertex in the Euler tour? And that is node 7. So what we want to do is to simply shortcut and go directly to 7. So we remove this edge and remove that edge, and then we replace it with the edge going 6 to 7, then from 7 to 8, then from 8 we went to 9, from 9 we went to 10, from 10 we went to 11. Now from 11, rather than going back to 9, we want to go directly to the next unvisited vertex 12. So I'll remove these two edges and shortcut by going directly from 11 to 12. Then I go to 13, then I go to 14, and now rather than coming back to 3, I want to go back to the starting node 1. So I will remove these two and shortcut it and replace it with that. Okay? So that gives me my final tour by replacing the Euler tour by a tour that visits every vertex exactly once. Now notice that we in this case added these 3 new edges. So what can we say about the cost of this final solution? So first of all, the observation is that the cost of final solution can be bounded in the following way. The cost of going from 6 to 7 is surely less than the cost of going from 6 to 7 via 4, right? So this is something as basic as known as a triangle inequality, which says that the cost of going directly from I to j is always less than the cost of going via some vertex. Now there exist situations where this might not hold. So for example, let's say instead of modeling distances, we were modeling airfare costs, right? And it's possible, for example, if I say I want a direct flight from Washington DC to San Francisco, they say, well, this is going to cost you $600. And it's possible that if I buy a ticket that routes me through some other city, which is not a direct flight, but a flight with one change, the cost could actually drop. So it could be cheaper. So obviously, like I'm saying, there are some contexts where the triangle inequality assumption does not hold. But for most travel time metrics as well as distance metrics, triangle inequality holds, and that's the assumption being made in this algorithm. These results only apply if triangle inequality holds. So if triangle inequality holds, then the shortcut at 6, 7 is no more than 6 to 4 plus 4 to 7. And the same thing happens here. The shortcut of 11 to 12 does not cost more than going through 12 via 9. And the same is going from 14 to 1. It does not cost more than going from 14 to 3 and then to 1. So now that we have this final solution, what we can indeed claim, let me erase this, what we can indeed claim is that the cost of the final tour is no more than the cost of the Eulerian tour. So what we have now is that the cost of our final solution, again assuming triangle inequality, is no more than the cost of the entire graph G prime. G prime was the graph that we got by taking the union of one minimum spanning tree and one matching. Okay? So this is no more than the cost of the minimum spanning tree T plus the cost of the matching M. And what was the matching M? The matching M was the cost of the minimum weight matching on the subset of odd degree vertices in the tree T. So obviously it depended on what T contained. Okay. Optimum solution. We don't know that yet. Okay. So how are we going to prove? So what is our goal? Our goal is to prove that the cost of this final solution does not exceed 1.5 times the cost of an optimum solution, right? And in general, we have no idea what this optimum solution is because that's the part that is NP hard to compute. So now let's imagine for a second an optimum solution in this graph. So there is some optimum traveling salesman tour in this graph, agreed? So let's draw a picture of it, even though we don't actually know what this tour is. This is simply some sequence of vertices of some permutation of visiting all the nodes in some order. And if I look at this optimum tour, and let's say I just go to some edge and I delete this edge, okay? This remaining path visits all the vertices, and notice that this is a spanning tree in the graph because it's connected and every node is visited. So what does that tell us? That by deleting any edge, in fact it didn't matter which edge we remove, but deleting any edge in the optimum solution, I can get what is known as a Hamiltonian path that visits all the node vertices of certainly cost less than the cost of opt because we deleted one edge. And this is also a spanning tree in the graph. So what this tells us is the cost of this tree T, which is the minimum possible spanning tree among all possible spanning trees in the graph, is surely less than equal to the cost of the optimum, right? So I hope this point is clear because all we are saying is that I can take the optimum solution, throw away some edge, I will get a tree that is a valid tree in the graph, and if T happens to be a minimum spanning tree in the graph, then this tree is only cheaper than that optimum tour. So that allows us to say that this cost of T is certainly not more than the cost of opt, right? So the next step that we have to prove is the cost, how to bound the cost of this matching M. So we want to be able to prove that the cost of the matching M does not exceed the cost of half opt. Okay, so let's talk about that next. So so let's go back and think about this optimum tour. Now, we had initially marked out some vertices as being red vertices in that MST of the vertices having odd degree. In this optimum tour, let's think about what those vertices are. It could be that this is a red vertex, namely that when we computed a minimum spanning tree, this node had odd degree, and maybe this node in the tree T had even degree, this node had even degree, and then maybe this node had odd degree in the tree, this node had odd degree in the tree, and so on, right? So we will skip over some nodes, and then there are some set of, obviously an even number, in this case 4, and maybe these two are odd degree vertices in the tree, and maybe that's the set S, right? So there's clearly some set of S of vertices that we identified, which were the odd degree vertices in the tree, and now all I'm saying is imagine marking out those red vertices on this optimum tour. Okay, and we're almost done now. Notice that if this is the set of odd degree vertices, there are two possible matchings that we can generate. So let's just simply number these nodes 1, 2, 3, 4, 5, and 6. I'm just numbering the red nodes in order in this optimum tour. Remember that we don't know the optimum tour, but we can still imagine it's just a thought process. And now I could find one matching by taking every odd numbered vertex in S and matching it with the vertex ahead of it. So namely, I could take 1 and I could match it with 2, and I could take 3 and match it with 4, and then I could take 5 and match it with 6. Okay. So that set of dashed edges gives us some matching M1, right? Now notice something, that M1, which is the cost of directly connecting 1 to 2, is no more than the cost of this path, again by triangle inequality. So the dashed edge, which is the direct edge connecting 1 and 2, is no more than the length of this path going via some other nodes. The same thing when we connect 3 to 4, this matching is no more than the cost of this. I drew it this way, but actually it's just a direct 3 to 4 edge. Okay. Now we could also imagine a new matching M2, the second matching M2, which is by taking every odd vertex and connecting it to the node behind it rather than ahead of it. So we would connect 1 with 6, we would connect 3 with 2, and we would connect 5 with 4. Okay, that gives me my second matching M2. And again, notice that the cost of M2 can be bounded by the portion of the optimum solution in the tour that connects those two vertices. So the cost of going from 4 to 5 directly can be upper bound by the cost of going via this node. Now what can you say about the total cost of M1 plus M2? We can say that the cost of M1 plus M2, as you can see by this picture, mathematically cannot exceed the cost of the optimum solution, right? So this tells us that the cost of one of these two matchings, because two of them put together is no more than the cost of opt, that the cost of the cheaper matching between M1 and M2 cannot exceed 50% of the cost of opt. So namely, the cost of the minimum of M1, M2, I'm just writing M1, M2 to denote the cost, is no more than half opt, right? Because both of these simultaneously cannot exceed the cost of half opt, because otherwise this inequality will be violated. So the cheaper one is at most half opt, but recall that once I fixed the subset S of vertices, we went ahead and actually found the minimum weight perfect matching in the graph on S. So whatever matching we found, which was part of the cost of the final solution, is surely cheaper than either M1 or M2. This is just one particular matching. So the cost of the minimum weight perfect matching, cost of M star, does not exceed the cost of the minimum of M1 and M2, which is no more than half opt. And that finally gives us the bound that we are looking for, that namely the cost of final solution, which does not exceed the cost of G prime, is less than or equal to the cost of opt. So the first term is coming from bounding the cost of the minimum spanning tree, and the second term is coming from bounding half of the cost of opt, which is the cost of matching. And we know that our cost of the final solution together does not exceed 1.5 times opt. So that's how we get this bound, that the cost of the tour found by Christophilus algorithm does not exceed 1.5 opt. People don't believe that this is the best possible bound. So for general metrics, still I believe this is the currently best bound known. For special kinds of metrics, a lot of progress has been made and bounds better than 1.5 have been found. The general Harry-Karp conjecture was that the right answer or the approximability for this problem should be roughly somewhere around 4/3, but we don't know how to get there yet. Okay, so let me stop and get some water, and then we'll continue with the new problem called vertex covered imminent. Thank you. Welcome back, everyone. I'm going to continue the second part of this lecture. So today, the rest of the lecture is going to talk about a problem known as minimum vertex cover. So what is the minimum vertex cover problem? So let's write it first mathematically and then discuss an example. The minimum vertex cover problem says that I'm given a graph G with a vertex set and an edge set. In the simplest form, let's assume it's an unweighted, undirected graph G, and the goal is to find a subset S of vertices such that for every edge, for all edges E of the form x comma y, we have the property that x belongs to S or y belongs to S. Okay. So in other words, we want to find a subset S of vertices in the set V such that for every possible edge in the graph, at least one of the two endpoints belongs to set S. Of course, we could take S as all of V and this property is to be true. So the interesting problem is to minimize the cardinality of S. Okay? So I want to find the smallest subset of vertices such that every possible edge is covered. So for example, if I have a graph that maybe looks like this, then we could say if I pick this node, then that certainly covers these three edges, but these two edges are still uncovered, and we could pick this node and then cover all of the edges. So these two nodes would form set S, and all the edges in the graph are covered. Okay. Now, of course, we could take all four nodes or some subset of three nodes and cover all the edges that way, but the goal is to minimize the size of S. In this case, these two nodes gives you an optimum solution. If you try to pick this pair of vertices, notice that this edge would still be left uncovered. So this is the minimum vertex cover problem. And again, even though it looks like a very simple problem that says that just pick nodes to cover all the edges, the problem still turns out to be NP hard. So there is no known polynomial algorithm to find the minimum cardinality set S that covers all the edges. And this is a very classic problem which is very well studied. And after talking about the basic problem, we'll also discuss one small generalization where all the vertices have some weight. So there is a weight function associated with every vertex V. I read a little v to denote vertices. So there's a weight function. Let's assume for simplicity these weights are non-negative. And then rather than minimizing the cardinality of S, the goal is to find the subset S to minimize the sum of the weight of all vertices in the set S. Okay, so our goal should be to find. So, for example, in that case, it's possible if let's say this node is very expensive, maybe has cost 100, this node has cost 30, this node has cost 10, this node has cost 5, that maybe the minimum weighted set of vertices has 3 nodes in it. I will drop this one because that's too expensive, has cost 100, and include these two. So this could be, for example, a minimum vertex cover of size 30 plus 10, which is 40, and we know that these two alone don't cover all of the edges. This edge will be left uncovered. So if I add that node of cost 5, then we get a solution of cost 45 that covers all of the edges. So there are sort of two questions here. One is the basic problem when all the weights of nodes is 1, and one is a more general problem where there's a non-negative weight function for every vertex in the graph, and I want to find the minimum weighted set. So let's talk about both of these separately. So first, let's focus a little bit about the basic question. The basic question just wanted a minimum cardinality set S of vertices so that all the edges in the graph are covered. And the first algorithm that you think of for this problem could be the following. I could take the graph and I could say, okay, so I want to pick few nodes to cover all the edges. What is the most natural thing to do? The most natural thing to do is to simply pick a vertex of maximum degree. So if I add this node to S, I will get to cover all of the edges incident on this node. And that will be the first node I add to S. And after all these edges are covered, we can delete all these edges from the graph. And now in the remaining graph left, after I cut this node out, I will again repeat the same algorithm. I will identify a vertex of maximum degree, and then I get to cover all of the edges incident on that node, and I keep running the algorithm that way. So that's sort of a classical greedy algorithm. The only problem with this algorithm is that there are actually some pathological examples where this algorithm behaves poorly. In particular, we talked a little bit about this approximation, or the notion of a factor 2 approximation. And one of the goals that I want to prove now is to show you a very simple algorithm where the cost or the cardinality of the set S produced by the algorithm, I don't need to write cost, I just said the cardinality of set S does not exceed twice the cost of an optimum solution. So opt simply refers to an optimum subset of vertices that covers all the edges. So that's our goal. Our goal is to find an algorithm with this property. This greedy algorithm I described to you, however, does extremely well in practice. In practice, for most graphs, if you try this algorithm, it might even find an optimum solution or close to optimum solution. However, it turns out that there are actually some pretty bad examples for this particular algorithm. In particular, there is no constant alpha for which we can prove such a property. So namely, you can pick any alpha, any constant alpha, and there are graphs for which, if you run this greedy algorithm that I described to you, the ratio of the cost of the solution found by the algorithm to the cost of the optimum solution are in fact going to exceed alpha. So it tells you that not only can you not get a 2 approximation, you are not even getting the 3 approximation or a 4 approximation or any constant alpha for that matter. For this very natural algorithm which does extremely well in practice. So of course in practice what we would do is we would run the greedy algorithm. We know in most of the time it will do well, but there are some bad examples for it. And then we could run also the algorithm I'm describing to you, and in practice we could just take the better of the 2 solutions. And then we are guaranteed to get a 2 approximation, and maybe the greedy will do a lot better than the algorithm I'm about to describe to you. So the algorithm I'm about to describe to you does the following. It says that just find a maximum cardinality matching in the graph. So the algorithm is very simple. I think the algorithm is due to Gavril. The algorithm says find, in step 1, find maximum cardinality matching. Let's call this M star. Okay. So we find a maximum cardinality matching M star. What do we know about it? So I have a graph G, and I found this maximum cardinality matching M star, right? And of course, this matching may not be a perfect matching, and there may be some unmatched vertices left behind. Okay, so these vertices are the vertices that are not matched for the matching. The first observation is that, so what is our final vertex cover? S consists of the set of all matched nodes. So it's very easy to define what S is. It's all the matched vertices. So the first observation is that S is a vertex cover. Okay. Now this is very easy to see. Why is S a vertex cover? The claim is that all the edges in the graph are covered once we pick all the matched vertices. So suppose S is not a vertex cover. What it means is that there is still some uncovered edge. Now since we've chosen all the endpoints of the matching in the solution S, that means the only nodes not selected are the unmatched vertices. But if S does not form a vertex cover, it means there is some uncovered edge which, let's say, connects 2 unmatched vertices. Can such an edge exist? The answer is no, because if such an edge existed, then this edge could have been added to M star, and you would still get a matching, giving a contradiction to the fact that this is a maximum cardinality matching. Okay? So we do know that S is a vertex cover. Now, what is the size of S? The cardinality of S is clearly exactly twice the cardinality of the matching M star. Okay, because we are simply picking for every matching the two endpoints. So the number of nodes that we end up in S is exactly twice the cardinality of the matching. The cardinality of the matching is simply the number of edges of the matching. Now our claim is that this is less than equal to twice the optimum solution. And again, this is very easy to see. Why? Think about this matching. So in this graph, I showed you that this matching had 6 edges in it. So there was a matching edge 1, edge 2, and so on, right? So there were 6 edges in the matching, 1, 2, 3, 4, 5, 6. Now imagine the optimum solution. We don't know what it is, but it's some optimum subset of vertices. So let's ask the following question. The optimum solution somehow has to cover this edge, agreed? In covering this edge, it has to pick either the left endpoint or the right endpoint. So the optimum has to say, I pick this, or maybe the optimum picks both. Right? Now notice that no matter what other edges we are able to cover by picking either one or both of these vertices, we are not going to be able to cover any of the other edges in the matching. Why? Because these edges don't share endpoints. So again, if I go to this matching edge, I say I have to cover either this endpoint or that endpoint by the optimum solution. So one of the two endpoints has to be covered, and the previous choice that we make does not help us in any way in covering this edge. And similarly, so for every edge in the matching, we can argue that at least one of the endpoints has to be chosen. This means that the matching size is a lower bound on the optimum solution size. So that's it. That gives us a two approximation. Now I want you to think about this algorithm a little bit. Why? Because in the proof of this algorithm, nowhere did we actually need the fact that it's a maximum cardinality matching. We did use it in the argument that this edge could not exist, which was an uncovered edge. However, something weaker will suffice. What I mean by that is that if I find matching M star, which all it needs is find a maximal matching M star. Okay? And the same proof goes through. So what is the difference between a maximum cardinality matching and a maximal matching? So I'll show you by a simple example. Suppose this is my graph, right? Suppose that's my whole graph. What is a maximum cardinality matching? A maximum cardinality matching would pick this edge and this edge. And that's a maximum cardinality matching. And what would our vertex cover algorithm do? Our vertex cover algorithm would say, take all of the matched nodes. So basically, we'll end up selecting all the 4 vertices in the graph as our vertex cover solution. That's not very interesting because we've chosen the trivial solution of picking all 4 vertices. And we're sort of hiding behind the fact that this solution is a good solution because the matching has size 2. So we know that there's a lower bound on the optimum solution of size 2. The optimum solution has to pick at least 2 vertices. Namely, to cover this edge, some vertex has to be chosen, and to cover that vertex, cover that edge, some vertex has to be chosen, and these two sets do not overlap. But notice that if I found a maximal matching M star, what is a maximal matching? A maximal matching is a matching just with the property that no other edge can be added to this matching, still keeping it a matching. So a maximal matching, for example, could include only that middle edge. That is a maximal matching. Why? Because if I try to add this edge to the maximal matching, I will lose the property that it's a matching. Or if I try to add that edge to the matching, I will lose the property that it's a matching. So it turns out, for the argument that I gave you earlier, that picking all the endpoints or all the matched vertices of this maximal matching, that suffices. The proof works, because if there is any unmatched edge, uncovered edge left, then this would not have been a maximal matching. Now the maximal matching hopefully is much smaller than a maximum cardinality matching. So even though this has the same approximation guarantee of the factor 2, in practice this algorithm could be a lot better. In fact, our goal should be to try to find a maximal matching which has as few edges as possible. That should really be our goal. If we can find a maximal matching that has few edges, unfortunately that's a hard problem in itself, but we could design some heuristic to find a maximal matching with few edges. Then that heuristic, for example, I think has the potential of doing extremely well in practice as well, and also comes with the factor 2 guarantee. Okay, so much about vertex covers. Let's move on to a slightly more general problem. of minimum weighted vertex cover. And I want to talk about this because it actually leads to some very, very interesting research that you can take whole courses on. But there's some very, very powerful ideas that were actually developed in the context of vertex cover. And it's a classical problem, and that's why I want to talk about it. So the generalization we're talking about is that we're given some graph G with vertices and edges, but now there is a weight function that maps all the vertices to non-negative real, so I just write R0, so every node has some non-negative weight, and the goal is to find again a vertex cover S of vertices to minimize the sum of the weights of all the nodes in S. So that's our objective function. We want to find a minimum weight vertex cover, and the question is, how do we do this? So this obviously is a generalization of the question we saw earlier, and we have to develop an algorithm which is a little bit following problem. Suppose I create some variables x sub v. So this variable, let's imagine for a second, is a binary variable. So its value is 1 if and only if v belongs to the set S. So it is 0 otherwise. So we're trying to capture subsets S of vertices by defining this binary vector. So let's take, for example, a simple graph that we had before of this type, where I have vertices A, B, C, and D, and we're going to have variables x sub A, x sub B, x sub C, x sub D. Okay. So for example, if my vertex cover has vertices A and C in it, we will simply say that xa is 1, and xc is 1, and xb and xd are 0. So this binary vector would be like an indicator vector for telling us which vertices belong to the subset and which vertices don't. In our previous example, I had given one of the nodes very high weight, and suppose we were trying to capture a different solution which did not include vertex C but included B and D, and maybe that was an optimum solution. Then that would correspond to the vector where xa was 1, xb was 1, and xd was 1, but xc was 0. So again, the point is that by creating a Boolean variable or a binary variable for every possible vertex in the graph and saying its value is either 0 or 1, we can exactly capture different subsets S in the graph. Now so far we haven't really done anything. All we've done is sort of created some notation, and of course trying to enumerate over all possible subsets S in this graph is not very productive, because I have 2 to the n possible subsets here, and again there's 2 to the n possible 0, 1 assignments to these Boolean variables. So we haven't really made any progress. But let's try to think about how to capture this a little bit more mathematically, and we can capture this by the following integer program. I can say minimize the summation over all vertices x now in the set V of, sorry, let's not use x, let's use u, x sub u. So remember, x sub u is a 0, 1 variable which tells us whether u is in the set or not in the set, and I will take the product of xu with the weight of vertex u. Okay? So if u is not in the set, then xu is 0, and the objective function, the contribution of the weight of the vertex u is 0, because it's 0 times the weight. If the variable xu has value 1, that means it belongs to the subset S, then 1 times the weight of the vertex will give us exactly this node's contribution to the subset S. So this objective function will exactly capture the weight of some subset S of vertices, exactly the subset S for which the variables are set to 1. Now, but of course, if I just wanted to minimize this function, I could simply set all the x variables as being 0, and I'll get a very cheap solution of 0 cost. So we want those x variables to satisfy some constraint. In particular, we will claim that for all edges of the form a comma b, we want x sub a plus x sub b to be greater than or equal to 1. Okay. So what we are saying, in other words, is that for every possible edge, I want to make sure that one of the 2 endpoints is selected in the subset S. Of course, it could be that both xa and xp are 1, in which case the left hand side is 2 and the right hand side is 1. But the key point is that both of them simultaneously cannot be 0, otherwise this is an uncovered edge. And we have the condition that xa is either 0 or 1. So this is what is known as an integer linear program. It's an integer program because these variables are required to be integral. It's a linear program because I have linear constraints and a linear objective function. And if we could say if we solve this problem mathematically, then in some sense we will end up solving the vertex cover problem. It turns out that this problem mathematically is a difficult one to solve. Not surprising, because obviously if there was a polynomial time algorithm to solve this problem, then we could simply have used that polynomial time algorithm to actually solve the vertex cover problem. And we know the vertex cover problem is NP hard, and this is obviously a more general problem, and so this is NP hard as well. But one thing that we can do is to solve this linear program by changing these constraints and saying that x sub a is at most 1 and at least 0. So I'm simply replacing this. In fact, I don't even need this upper bound. I can just say xa is non-negative, and that's good enough. There is never any need for making an xa value more than 1, because if xa is say 2, then I can always lower it to 1 and I will not violate any constraint because all the variables are non-negative. Now this makes the problem much, much simpler. For example, now that I'm allowing xa to take any non-negative real value, this becomes something called a linear program. Okay. Now linear programming is a lot easier than integer linear programming. In particular, linear programming can be solved in polynomial time. There's a variety of algorithms. There's an ellipsoid algorithm due to Kashian, there's an interior point method due to Karmarkar, and any of those two approaches can be used to solve linear programs. There's a very old simplex algorithm due to Danzig, which even though in the worst case is exponential running time, in practice works extremely well. And so any of those two approaches can be used to solve the linear program. And once you get optimum solution to this linear program, we somehow want to be able to map it to a valid vertex cover. What I mean by map it is the following. When we solve this linear program, in fact, we are not guaranteed that the values of the variables are either 0 or 1. So in particular, let me show you a graph where we will run into the following difficulty. Suppose in this graph, we write a linear program for the three variables xa, xb, and xc, and say that xa plus xb is at least 1, xb plus xc is at least 1, and xa plus xc is at least 1. If I want to find an integer solution, then the cost of the cheapest integer solution is going to have to include at least 2 of these vertices, even let's say if all the weights of the nodes are 1. So picking any one of these vertices would always leave one of the edges uncovered. So I have to pick at least 2 of them. So in the integer linear program, the optimum solution has cost at least 2. In the fractional version, however, if I relax that requirement and simply say xa is greater than or equal to 0, then what might happen is that in the optimum linear program solution, all of these variables could get the same value of 1/2, right? If they all get the same value of 1/2, notice that all these constraints are met. The sum of these two variables at least 1, sum of these two variables at least 1, and so on. And all the constraints are met, but this solution is actually cheaper. It has cost 1.5, half plus half plus half if all the weights are 1. Now, how are we going to round this solution? So the rounding algorithm is also extremely simple. The rounding algorithm does the following. So here's the linear program. The rounding algorithm says that we're going to define a subset S simply as consisting of all of the vertices u such that x sub u, the variable, is at least 1/2, right? So in this particular example, notice that all 3 nodes will in fact be added to set S, because all 3 variables are exactly 1/2, and so S includes all the nodes with value at least 1/2, right? Now, of course, in this example, all these variables have value half, but that doesn't have to be true. So, for example, there could have been some other structure in the graph here, maybe like that, and maybe this node had some value half, and maybe there was a node here, and then there was another node there, and maybe this node had value half. Actually, it's not interesting. Maybe I can make this 1, and this one could be 0. So there could be nodes with value 1 and 0 as well in the graph. I suspect I could actually lower, no, I can't lower that anymore because this edge would be uncovered otherwise. So that could be one possible solution that we might end up with. So in general, you can have any sort of fractional value, 0, 1, half, or others, but this specifies how to pick a subset of vertices. And the simple observation is that if you now look at the weight of all of S, which is the weight of all the nodes that we selected by this rule, it is very easy to prove that the weight of this S is at most twice the cost of the optimum LP solution, the LP that we wrote for this graph. Why? Notice that every node that I choose in S, suppose I picked a node of weight 100. Notice that the cost that we have to pay in our vertex cover is the full cost of 100, it's the full cost of this node, but its contribution in the linear program, because this node had fractional value of at least half, was contributing at least 1/2 times 100, so it's contributing at least 50. So our cost will at most double in this process, and our cost is at most twice the cost of the linear program. And the next observation is that the cost of the linear program is less than or equal to twice the cost of the optimum vertex cover solution. And that's also easy to see because the optimum vertex cover solution, the cost of opt, is in fact an integer solution and is a feasible solution for this linear program. It's just that it has values that are only 0 and 1, but it is a feasible solution for this linear program, right? Now this linear program is allowing other kinds of solutions as well. So when I optimize over these non-negative constraints for the x variables, this linear program is going to have cost at most the cost of opt, because the optimum solution is a feasible solution for this. But when we optimize, we are sort of allowing these fractional solutions, the cost could only come down, it can't go up. So that's what leads to this inequality, and that allows us to bound the weight of our final solution as twice the cost of opt. So this sort of shows you one way in which we can use this linear programming framework and then do this very, very simple rounding process to obtain a solution for which we can prove, even for weighted vertex cover, how to bound the cost of twice opt. But of course, there are lots of other still interesting things to study here, because if you think about the vertex cover problem, the set of constraints that we had there were incredibly simple. They had a very, very simple form. And you could say, do I really need to invoke the full machinery of linear programming to solve the linear program? And the answer is no. That linear program is a very special form, and there are very efficient ways of solving it. And in fact, that insight leads to some very, very simple combinatorial algorithms that in fact run in linear time and do not involve ever solving the linear program. But however, I think that's the subject of another talk, which involves something called linear programming duality, and that leads to an explanation for how or why many different algorithms that were developed for the weighted vertex cover problem, in fact, all have sort of a common basis and can all be explained in one unified framework. So maybe that would be the subject of the next lecture. I don't know whether I'm going to have time for that today or not, but and it also needs a little bit of background in LP duality. But if you're interested, certainly I can send you some notes to read up on about this topic. I have notes on my class webpage that discusses this in depth. All right, thank you. Hope you have a good workshop, and I hope to be awake tomorrow morning to answer the questions. Thank you so much. Bye.